Hi, folks. How are you doing today? Doing good, having fun with stuff. Life's nice. Gotta do laundry today, right?
Trying to survive the finals.
Trying to survive. What are you fighting with in terms of survival? What can I help with?
10.2 and 10.3.
Anything particular or just those are being scary?
Those ones have been really hard for me.
Anybody have anything more specific in those, or do you just want me to grab some stuff from those and play with them?
I have difficult time with the critical value.
Okay. So let me find one that includes. I'm in 10.1, that's why.
I think question 1 or 2 has a question with a critical value.
Yeah, I just have to move over to 10.2. I was in 10.1.
Maybe you could do one with the p-values too.
Yeah, let me do a critical value 1 and then do a p-value 1 to compare.
Okay, thank you.
Oh, my computer's being persnickety. There we go. Very persnickety. Okay. These questions can look a little bit long. They can be a little bit intimidating. So we want to take them piece by piece. So we wish to test the following claim, this alternative hypothesis, at a significance level of 0.005. We're given our null hypothesis of 0.78. And this is a proportion problem. So our assumption is that there is some, set of data where 78% of it has some quality, but somebody is claiming, so this is our assumption, that that's the truth, but there is a claim by somebody that that proportion is not equal to 0.78. Somebody thinks it's not true. So we want to figure out, okay, they're going to do a test. They go do a test and they grab a sample of this data. That sample is of size 612. It's a pretty big sample. And in that sample, there were 463 successes. We could combine those to get our sample proportion if we knew what 463 divided by 612 is. So 463 divided by 612 is 0.75. 0.75. I'm going to go 6.5. Now that 0.7565 is less than what the claim is, but the question is it significantly less? Is it less enough for us to say that the assumption is wrong? Because you don't expect your sample to be exactly equal to the population. You allow it to be a little bit different. But is 75 so unlikely, 75.65%, so unlikely that it makes that assumption look flawed? That's the idea here. Is that all fair and good? Okay. So, how stringent are we going to be about that? Well, that's what our significance level is here. And that significance level is really small. So we're being fairly stringent. So that's, good if we want to support the assumption, but it makes the claim hard. Now, what does this alpha represent? That alpha represents our critical regions. And in this case, our critical region is both the lower parts and the upper parts. Because this is a two-tail problem, it just says not equal. So it is a two-tail problem. So our goal is to figure out, again, under our assumption of 0.78, is the 0.7565 far enough out into these tails that we want to reject our assumption? That null hypothesis you can always think of as our assumption. How big are these tails that we have to land in to reject our assumption? That alpha is the size of those tails. And since it's two tails, they're adding up to the 0.005. So each one is 0.0025 and 0.0025. Good with that so far? So that's why this is a pretty stringent test, because that means that 99.5, so 99.5%, if what's the likelihood that if that assumption is true, what is the likelihood that we would get 75.65%? It's got to be outside where 99.5% of samples would land. So it's really like, is that probability of this happening by chance really small? We're talking really small. So this is a very, very stringent test. Cool. Well, it might be nice for us to know what that z-score is. That would tell us, instead of looking at that as the percentage, what percentage do we need to be at? How many standard errors from the mean do we have to be in that critical region, in the dark regions? And we've done that before, right? How do we find z-scores given proportions? We do our inverse. So our inverse norm, the proportion we want, 0.0025, with a mean, well, this is supposed to be a z-score, right? If it's a z-score, our mean is 0, our standard deviation is 1. Fair? When you do that, what do you get? Certainly over 2, not quite 3. Anybody want to tell me what you get when you do that?
Two,
I got, oh, sorry.
2.80. Well, 807. Well, that's what I
So
got.
if we round, how about 2.81?
Yeah.
That, and then of course that's down here, it's negative, right? So it probably said negative, but
Yes.
that one's positive, right? So that's your critical value. And that should be fairly reminiscent of finding critical value for a, if this said a confidence level of 99.5%, this is what we would do to find the critical value for how many standard errors out our confidence interval should be, right? So it's the same use of the vocabulary critical value. We're just using it kind of in a different, sort of in a different way. Mostly we're just, coming from the tail probabilities as opposed to from the internal portion. We're talking about being on the outside as opposed to being on the inside, but it's the same value. So for example, if this had to be, 95% in here, that would make the alphas equal to 0.025 and on each side, 0.025. And we know what that critical value is. That's our 1.96, right? So if our significance level had been 0.05, we'd have just used that 1.96. So it is that same critical value that we've been talking about before. How's that? Is that good so far? Cool. Okay. Sort of new to this section is the idea of finding the test statistic. Well, we have this is what we're using to test the claim, is this sample proportion of 0.7565. So it would be nice to know, well, where does that land in this distribution? Does it land before the 2.81 or does it land after the z-score of 2.81? Is it in the reasonable area or is it out in the critical region? We could do that by comparing what its probability is, but since we've got this z-score to compare it to, let's use that z-score for this thing. Fair? Almost fair. It's a little bit cheating because we technically want to find the t-score of this thing, right? Because it's a mean. But we find them in the same way. So our test statistic is, that's not how you're supposed to statistic. I should know how I'm supposed to statistic. Yeah. That's why I say stat. Our test statistic, I like missed the middle part and then threw an E on the end because I panicked. Our test statistic, in proportions, it'll be a z-score. In means, it'll be a t-score, but we find them the same way. It's just like it's always been, value minus mean. Wait, this is proportions, isn't it? Never mind. I got all excited about means. But okay, test statistic. Because this is a proportion problem, we are in means. Or sorry, are in Z's. But again, we find it the same way. Our test value minus the mean of our distribution divided by the standard deviation, which in this case is a standard error. Now our proportion here is that 0.7565. The mean of this distribution is that 0.78. Now you might be thinking, wait, that 0.78 is our proportion, not a mean. But remember, the mean of our sampling distribution is the proportion of our population, right? So that is a mu, 0.78, divided by our standard error. Our standard error is supposed to be PQ divided by the square root of our sample size. And our sample size was 612. And our P and our Q, this is where sometimes people make a little error here. That P and Q, again, should be the population P and Q. So it's our 0.78 and our 0.22. Fair? It's often nice to find that standard error separately, kind of go, well, as soon as we start looking at this diagram, kind of going, okay, what's its standard error? And going off and going, well, that's 0.78 times 0.22 divided by 12. And then anytime we need that standard error, we can stick it places. Fair? But if we work that out, we should be able to come up with the z-score for the test that was taken. That's why it's called the test statistic. It's the statistic, it's the value that demonstrates what our test says, what our experiment says. So find that value for me and we'll look at it. Certainly going to be negative because it's below the mean. Anybody got a value for that? I know that's a lot to type in. That's why I often find the standard error separately. But then you got to carry a lot of decimals. Frankly, the best thing to do is find your standard error and store it in the calculator, and then call it. So you're getting a lot of decimals.
I'm not sure if this is right, but I got negative 45. No, that's a lot.
45, yeah, it's way too big.
No, I got the same.
Negative 45.
I
Yeah.
got negative 1.3377.
Well, let's do it in parts and see what happens. Let's just do this standard error, see if we can come to a consensus on what we think that standard error is. So square root 0.78 times 0.22 divided by 612. That's a 0.0167. 0.0167.
Yeah, that's what I got.
Okay. So we've got 0.7565 minus 0.78 over 0.0167. 0.7565. I'm just going to do this in little pieces to make sure we're all happy. That top ends up being negative 0.0235 divided by 0.0167. So take that and divide by that. And I get negative 1.403.
Yeah, that's what I got.
Okay. But yeah, there are a lot of places to miss the parentheses on your square roots, do all kinds of ugly things. So I think really being careful and kind of doing that in pieces is probably nice. But we know it's a z-score. So something like, 44 standard errors below the mean, that is really far out. Now that can happen, but one of the reasons I think finding the standard error separately is helpful. That means that our, 1.6% is every standard deviation for a sampling distribution is 1.6%. So this would have to have a difference of 44 1.6%. It's nowhere near that far off. That makes sense. And again, it's not hard to have some little parenthesis issue, give an answer like that, but we got to look at that answer and go, as you did, go, that doesn't look right. Okay. So that is our test statistic, negative 1.403. So in our diagram, that's well in that normal region. If this is a z-score of negative 2.81, our test statistic of only 1.403, that's well inside that reasonable region. Fair?
Yeah.
So is it in our critical region? Our critical region, you have to remember, is the bad place. The bad place if you're the null hypothesis, good place if you're the completer. So hard to say which one's better, but that critical region is the part outside. So is it in that critical region? No, it is not. If it's not in the critical region, do we reject the null, accept the null, or fail to reject the null?
Fail to reject.
Okay, yeah, we fail to reject. We never accept anything. You never accept the null hypothesis. Because this value, the fact that that's in that region, doesn't mean the assumption's correct. We haven't proven that that assumption's correct. We just haven't shown enough to indicate that that assumption is wrong. Fair? So we never accept the null hypothesis. We either reject it or we don't reject it. And to reject it, you've got to be out in those little tiny tails. And we weren't in those tails. Fair?
So the tails is the place where our assumption is.
The tails are the place where our assumption fails.
Oh,
So
okay.
if you want to think of it that way, and I think that's very reasonable, this is, we assume, if what we assume is true, our sample values should land in there. Fair? If it's wrong, the alternative story, the alternative lives in the tails. Fair?
Is this for this specific case or for all of them?
All case. That's null hypothesis testing. The null hypothesis is, if the null hypothesis is true, we should land in the middle. If the alternative hypothesis to be supported, we never prove anything. We support or don't support. or reject or don't reject. The alternative hypothesis lives in the tails. Now, sometimes it's only one tail, not both. This is a two-tail problem, so our alternative is both tails. That's why we had to split it in two pieces, half in each. If it's a one-tail problem, you get all of the alpha, all of the significance level in one tail. But you're still, the alternative is in that tail. The null hypothesis, the assumption, is everything else. Cool?
That was helpful. Yeah, thank you.
Cool. There you go. So final conclusion. So we didn't find enough evidence, so it's one of those two. Not sufficient evidence to warrant rejecting the claim that the population proportion is not equal to. No, we weren't trying to reject that it's not equal to, so I don't like that one. There's not sufficient sample evidence to support the claim that the population proportion is not. So not sufficient evidence to say we're wrong or the assumption's wrong. And that these can be tough, you know, the figuring out what the wording is, because it's real specific. But you kind of want to look at that, look for those couple of words, either is significant or not significant, and then look at what are they supporting or what are they rejecting. So, you know, not significant to reject sounded good, but not significant to reject what? The proportion's not equal to the 0.78. This is not sufficient to reject the alternative hypothesis. Well, that's not what we're not rejecting. What are we not rejecting? We're not sufficient to support that it's not equal to that. So this is not sufficient to, I'm going to say, like or support the null or the alternative hypothesis. I would have liked one that said there's not sufficient evidence to reject the null hypothesis. That's what I'd want to find, but it's not on the list. Fair? The closest one, there is not sufficient evidence to support the claim, to support the people who are claiming that the assumption is wrong. Now, I kind of like the problems presented this way because it's, you know, those diagrams are familiar. Critical value, we've been using it from a slightly different perspective, but it's the same critical value we've been using. The language for test statistic is a little bit new, but the idea that, well, that's just our Z-score for our thing. You know, the language and the kind of diagrams are fairly familiar here. It's not too different, hopefully. But then, as I forgot who asked that, but then we get p-value questions, and the language kind of changes a bit. And the process we're going to use changes a bit, but I want to hopefully show you that it really is asking the same exact type of question, just in a slightly different way. Before I do that, any questions about that first problem? Christy, you said you were fighting with the 10.2 and 10.3 a lot. Is that helpful in kind of a layout? Okay.
So this problem is from 10.2 and 10.3, right?
Yes, this one specifically from 10.2.
Okay.
I
So-
did not look at, oh, sorry, it's a quick question. I did not look at 10.3
at is kind of similar to 10-2?
It is. It is. It's just, I think 10-2 is proportions and 10-3 is means,
Oh, okay.
but the logic is same logic. No, they both do
Thank you.
means.
Okay.
We'll look at what the difference is. Off the top of my head, they kind of all blend together for me. 10, 1, 2, and 3 is the language, some of these problems, and then some, the problems just get a little bit more involved as we go along. Oh, this is a mean problem right in front of us. So that's good, actually. Okay, we want to test the claim that the proportion of people who own cats is, oh no, it is a proportion problem, is 60% at the 0.01 significance level. So first, they want us to kind of put this in our notation for null and alternative hypothesis. So test the claim that the proportion of people that owns cats is different than 60%. That means that 60% is our assumption. I don't know where that assumption is coming from, but that's the assumption that they're giving. So if it's the assumption, that is our null hypothesis. That assumes this person's claim is incorrect. Fair? If we want to test somebody's claim, assume they're wrong, the burden of proof is on the claimer. Fair? So a null hypothesis is that the proportion, so it's a P, is equal to 60. 0.06. Fair? And somebody is claiming, as soon as we see a claim is our alternative hypothesis. So that's our alternative hypothesis. And our alternative hypothesis is not that it's greater than or less than 60. They're just saying the claim is that it's not 60. Fair? Now, if you're somebody who's claiming something in a null hypothesis, if you're trying to support the alternative, this is actually a disadvantage. Because notice up here when we did it, having it be a two-tail test makes each tail smaller, right? So it's harder as the alternative hypothesis to land in those tails because those tails are half the size because they're split on both sides. Fair? If you wanted to make claiming that this proportion of cats is different than 60, you'd be better off claiming it's either greater than or less than, because your tail ends up being twice the size. Fair? So it might seem like, well, why are they just saying like not equal to? That's kind of a, easy and kind of lame thing to say, I think. It just says you're wrong. It doesn't say it's less than, doesn't say it's more than, it just says you're wrong. That's actually very disadvantageous if you want to have enough information that you're trying to claim more or less in practical applications. Fair? But again, this is doing two-tail. I mean, this happens, all the times in lots of applications. So it's not unreasonable. It's just from a trying to prove your claim perspective or trying to support your claim perspective, it's disadvantageous. Cool. But either way, it's that one. It's the H, they use the H1 language there and the HA language up there. Oh, okay, they're using both. That's good. And as we've been talking about, this is a two-tail test because it doesn't matter if it's above or below. You guys know I'm always going to draw our sampling distribution out. So the mean of that sampling distribution is the population proportion, or at least its assumption. And we're two-tail, so we're going to be two tails. Cool. So I suppose we figure out how big those tails are. Those tails are both 0.005, half of our significance level on each side. Again, if it was just a one tail, then the one tail we're looking for gets to be the whole 0.01. Makes it quite a bit bigger. Now we could do this problem exactly like we did the one before. We could find that critical value. This is a 99%, so we actually kind of know what that is. It's like 2.56 or something like that. So we could find that critical value. We could find the test statistic for this 54%. We could do it just like the problem before. But that was a fair amount of work, wasn't it? That was a fair amount of work. The p-value essentially allows us to speed that up with these things. Now, we don't have to use these things to find a p-value really, but sure makes it a lot faster. Fair? So, again, that 54% is a sample proportion. What, a 54? So 0.54. And the question is the same as the one above. Does that 0.54 land in the reasonable place, the null hypothesis region, or does it land in that tail? If it lands in the tail, then it supports rejecting the null hypothesis. If it lands in the kind of big open region, then it fails to reject the null hypothesis. Right? Same thing as the problem above. The only difference with p-value as opposed to critical value and test value is we calculate the probability instead of the z-score. So we find where it lands in terms of the probability. So is the probability, is the area of the region larger than the 0.05? Or is the area of the region smaller than the 0.05? Now we could find those by finding the critical values, using our chapter 7 tools, find those probabilities. But again, we're not going to, we're going to use the shiny boxes instead. Right? So we're going to go to our, go to our stats test. So your stats, and then go over to tests. And this is a one variable proportion problem. So we're going to grab one proportion z test. And on mine, that's number 5. I don't know what it is on yours. Is it number 5 on yours?
Yeah.
Okay. Now that wants a couple of inputs. So one proportion z test. It wants p, it says p naught, but that's the p for the null. It wants x, it wants n, and it wants to know whether it's one tail, two tail, or one tail, two tail, one tail, left tail, or right tail. So tail type. So what's our null proportion? Is our 0.60. Our X value, notice in the one above, we were told X, we were told how many yeses there were, right? And we had to figure out the sample proportion. Here, it's backwards. We're told the sample proportion. We weren't told how many actual successes there were. But can we figure out how many successes there were?
Yes.
Yeah, the number of successes is 54% of the 200. So they're making us find that value. Sometimes we have to calculate the proportion. Sometimes we have to calculate the value. Depends on what information we're given. So what is that, 108?
Yeah.
So that's 108. The sample size is 200. And this is two tail. So I'm going to put that all in. 0.60 with an X of 108. The sample size of 200. And it's a two-tail test. And that should output a Z value. Now, that is our test statistic. So if you didn't want to find your test statistic by hand, if you didn't want to do what we did up here, this test gives you that test statistic if you want it. But it also finds our p-value, 0.0832, and so on, 326. So how about 33? And it tells you the sample proportion, 0.54, and sample size again, for some reason. But those are usually the two that we want. In this particular question, we're asked for the p-value, so that's our p-value. But what does that mean? That's a probability. So that means the probability of being that value or greater was 0.0833. And the question is that bigger than our 0.05 or smaller than our 0.05? If it's bigger than our 0.005, then we landed in our null hypothesis or assumption region. If it's smaller than our tail size, then it landed out in our critical region. Not only is this bigger than our tail size, it's a lot bigger than our tail size. It's like 16 times as large. Fair? So having the true proportion be 60 and you get 54 instead, 54% instead, and somebody says, well, what's the chance of getting something so small? Yeah, it's 8.33% chance of getting something that small. It's almost 10%. That's going to happen all the time. That's going to happen like 1 out of every 11, 12 times you take a sample. That doesn't prove or make me worry about my assumption of 0.6 at all. Fair? So is that enough evidence to reject that 0.6? No, it's not even close. That seem reasonable? And again, we could have done that up here with more of our hand skills. As soon as we found this negative 1.403, we could have taken that negative 1.403 and done those, chapter 7 skills to figure out what the area of is below. And that area below would have been bigger than 0.0025. That area below would have been our p-value. Now we didn't because we weren't asked for it, but it would just have been one extra step here. The handy thing about the p-test is it does it for you. It does all those calculations we did above and just says, here's your p, and by the way, here's your test statistic if you happen to want it. Cool.
Yeah.
And it has a big advantage in terms of the z-score comparison, kind of comparing the 2.81 to the 1.4. It's pretty easy to go, well, oh yeah, that's a lot smaller than that. The 1.43 is a lot smaller than the 2.81. But people often find it more compelling to express it as a probability. So this p-value literally says, how unusual is this? Oh, it happens 8% of the time. Oh, 8% of the time, I'm not freaked out by that. It's a very kind of solid feel for how strongly did this test support or reject something. Particularly if your p-value is something super tiny, you'll say, hey, I thought these people were wrong, and I tested that claim, and I got a p-value of 0.00001. Wow, they were that assumption was crap. You reject the heck out of that null hypothesis, as opposed to just, oh, my p-value was on the line of my significance level. I needed it to be less than 0.05 and I got 0.04. Okay, so yeah, you supported them being wrong, but not with a lot of oomph. If you can show a small p, not only did my thing show that they were wrong, but look how much. So it makes for a very strong argument. That's why you often see the p-values given in arguments. But hopefully it makes sense why these are essentially the same problem. They're just coming at them in slightly different ways. This problem is asking to compare the proportions. This problem is asking you to compare the number of standard errors. How far out are we in terms of standard errors versus how far out are we in terms of probability? It's the same location, same place, just which one are you asking? I forgot who asked about a p-value one. Who asked that? You don't remember either.
That was us.
Did that help? That make sense?
Oh yeah, for sure.
Okay. So let's do this.
Chat unless.
Oh, I could not see the chat. Thank you, David. P-value by hand, yes. Again, we could have found the p-value for this one because I'm just redrawing this because my picture's getting a lot. We've got a mean of 0.78. We've got a standard error of 0.0167. And we've got that test statistic of negative 0.14, yeah, negative 1.403. If we were back in chapter 7 and I said our mu was 0.78, our standard deviation, though this time it's called standard error, but it's still a standard deviation, is 0.0167, and asked you to find the proportion or the probability or the area under that portion of the curve, you could do that, right? You would either use your normal distribution tool in the calculator, or if you wanted to be a little more hands-on, you would go to your table, and that's your z-score. So your z of negative 1.4 and 0, because that's as far as the table goes. That area is a p-value. So it would have been one more step, but it's a step that we have set up. As soon as we have this test statistic, going from that test statistic to the p-value, those things are chapter 7 interchangeable, you know. Somebody might want, tell me this, you know, test statistic, because that's the way I like to hear that information. Somebody else say, I want the probability. Okay, because that's how they want to hear the same information. It's the same information. Cool. So we could have done all of that down here. We also could have found this test statistic using the p-value tool, because as you saw, it gives us both of them. Because it might as well, it's the same information. So let's get a little sneaky here. How's our time going? Oh, no time's doing good. I'm going to give you guys a couple of minutes. And say, try that.
Can you make that bigger, please?
Oh, I tried to make it bigger. Just recognize that the reject, the what is our decision at the bottom is going to be the end of that. And as usual, I'm going to suggest draw that diagram. Excuse me. Yeah, I can't think of a compelling reason to not draw the diagram. Excuse me. Oh yeah, it is means in 10.3. So yeah, it's the same. It's just means instead of proportions. Did we notice that that was a one tail problem? So it's only that one tail at the full size. Now, if we want to find that test statistic, we can do it like we did in the first problem, or we can do it like we did in the second problem. Which one do you want me to do?
Second problem.
Second problem? Okay. So the second problem, we would just go to our one, write that bigger, our one proportion, one population or one sample, one population. We're not comparing two populations. We're looking at what's happening in one population. So that's why it's the one instead of two. And prop because it's a proportion. So our one proportion z-test. And that's going to want our null hypothesis. It's going to want the number of successes and the number of trials. It'll figure out the sample proportion by itself. And then this is one tail and specifically left tail.
One quick question.
Yep.
So, if we're not totally confident if we got the left tail test correct, can we just confirm that by checking if the z-score is negative?
Yes.
Okay.
But also, the arrow goes left, right?
Right.
So no left.
Just on the off chance you put something in the calculator and didn't bother to check until you wrote it all down.
Right. Then you can go, why is that way? Oh, okay. Yep, that happens. I just always hated the alligator eats the bigger one stuff, with greater than less. It's an arrow. It's been an arrow for thousands of years. Only about 80 years has it been an alligator that eats the big one. No, P is to the left of 0.48. That's what it says. Been that pet peeve. Oh, what did I put in weird? Oh, didn't put in the right sample size. Okay, so the nice thing about doing it like the second problem is you're just asking the shiny box, right? So it's just, what does the shiny box say? Yeah, it won't zoom, that's okay. But the shiny box says that test statistic, that's our Z, is negative 2.32. And of course, the hard part about that is knowing that that's what your Z is on this. And the p-value is 0.01012. And it gives this point, it tells you what that sample proportion is. And it reminds you what the sample size was. So, okay, that's our p-value. Our p-value is 0.01 and a little bit more. The question is, we've got p-value is bigger than our significance level. Thus, what does that mean?
It means that it's inside the null.
It means it's inside the null, as we've been talking about that, inside this reasonable region. That means it's out here somewhere, right? Our p-value is bigger than the tail. Thus, it's greater than, and if it's greater than, if it's bigger than the tail, thus outside the tail in the null region, does that mean we accept the null? We never accept the null. They put that there just to drive you nuts. Never click on it. We fail to reject the null. And one of the nice kind of analogies we often give to this is court cases. If you go into a court case, the assumption is that you're innocent, right? So the null hypothesis is you're innocent. The claim that you committed a crime, that's the alternative hypothesis. And the alternative hypothesis has to be shown. You don't have to prove you're innocent. They have to prove you're not, right? And if they don't have enough evidence to convict you, what do they say? What's your verdict if they don't have enough evidence?
They don't say you're innocent.
They don't. They say you're not guilty. There's not sufficient evidence for us to convict you of this crime. They do not find you innocent. Fair? So that this accept the null is essentially the null hypothesis version of you have proven your innocence. You haven't proved, we often say that conversationally, but you haven't. You can then file a civil lawsuit against the state to legally find you innocent, but that switches the burden of proof onto you and is rare. People often, it's not terribly uncommon. People have done it quite a bit, but it's much more rare because that burden of proof flips on you. So that's and your book talks a little bit, we don't go too big into it here, but it talks about type 1 and type 2 errors. And if you go more into hypothesis testing, we'll talk a lot more about that. And that's kind of the whole, do we want to err on the side of rejecting the null, or do we want to err on the side of accepting the null? Essentially, do we want to err on the side of not convicting innocent people, or do we want to err on the side of convicting innocent people? Which error are we happier with? Anyway, so there's a whole set of comparisons to this type of testing and a lot of other things we do, just to give some perspective.
I have a quick question about this in relation to the test.
Yes.
Because I remembered you saying that like chapter 10 is kind of going to be more of like a general, make sure you understand it all as far as what's actually on the test. So are we going to have like calculations as far as like the test statistics and p-value and all that good stuff on there?
My intention is for them to be, a lot like these are, as opposed to ones, like these where you've got to, use all the raw data and,
Okay, I get what you're saying. It's
Yeah.
already kind of provided instead of us having to search for it like the other kind of problems we've been doing.
yeah. And really, even this one would be a little bit like, that's a lot. Just kind of ones like the couple that we've done that's like, here's your basic information, find your either your tests or your P's or maybe both, and just kind of, do you know what it means in terms of rejecting or not rejecting, as opposed to getting really big into a word problem that you're having to translate and data you're having to use raw and
Okay, awesome. That's all I was wondering. As I started to get into chapter 10, I was like, whew, some of these are lengthy, the questions they ask in there. So thank you.
Yeah. And as I said, null hypothesis testing is a big field, because it is used in so many disciplines in so many different ways. So this is really supposed to be just an introduction to it. Those of you who go on into statistics and data analysis will do deep dives into it. But enough of you will see research and survey information that will throw out P's every once in a while. And really, if you take nothing away from this other than small p-values mean strong argument, then you've taken something good from it. Fair?
Actually crazy how much statistics relates to everyday life. Like one of my friend's dads is a statistics teacher, and
Mhm.
so like when the election came along, he was putting up all these statistics and like kind of explaining it all to everyone, and I was like, it's really cool I'm in a statistics class as kind of all of this is happening. It's great
It
for
is.
the world.
Well, and one of the fun things you'll hopefully notice, or hopefully have noticed, is now that you kind of have some of this vocabulary and some of these tools, you start to hear it more often. You start to see where people are trying to express things this way, and you're like, wait, I know more about what that means now. So hopefully that's happening and will continue to happen in lots of respects. I gotta let you go so I can get to the other class, but did we talk yesterday about meeting tomorrow in case you guys have any other questions?
Yes, we did at 11:40.
11:40, okay. Then I'll see you guys then.
Can I have a quick question real quick?
Yep.
So for the final exam, are we going over chapter 9 and chapter 10? That's what it's going to be on.
I believe your final is comprehensive. Does it say that, or does it say just chapter 9, 10 test?
I think it says 2, 3, and 6 through 9.
Let's see. Yeah, the test 3 is over chapters 2, 3, and 6 through 9. So basically comprehensive, except 4 and 5. We didn't really do 4, and 5 is just some language so we can do 6. But like 2 and 3, if you remember, were things like what's a histogram and finding a mean. So that allows me to put questions on the test that say things like, what does standard deviation even mean? You guys know what standard deviation is. You know how to find it. I won't ask you to do it by hand. Find a mean, find a median. You might want to review the whole interquartile range stuff. But mostly by now, those questions are almost automatic, and you guys learned those things. So giving you a chance to get credit for that is good. And then some 6, 7, 8, 9 questions.
Wait, how many questions are going to be on the test?
74. No, like I think there's 15 or so.
Okay, cool. Just give you a heart attack.
You said
Yeah.
15, right?
Yeah, like 15. Give or
Okay.
take.
And I have the same question from Elena, I think. How long is going to be the test?
I think as I recall, it's an hour and a half.
Okay, and also, it looks like it's gonna open on Thursday and close on Friday. What time it will close on Friday?
11:59 at night.
Oh, at night. Okay,
You have all day.
all right. Thank you.
Sure.
Quick question. So you're gonna be here tomorrow at 11:40?
Yes.
Okay, thank you.
And can you post more reviews stuff over like 2, 3, like, well, especially we should just know, like, can you just post more on the review?
Yeah, send me a message. I'll try to find something I can put up. The good thing to look over are those old tests.
Okay, sweet.
But yeah, I can probably send something out. Something. I got lots of stuff, so I'll find something to send out if you want. But yeah, send me out a message, remind me.
Awesome. Thank you.
Sure, sure. Okay, I gotta get to that other class, but I'll see you guys tomorrow.
Thank you so much.
Thank you.